Hello, everyone. This is your lecture for Thursday, May 6th, Sound Part 2. Okay, so first slide here is a reflection of sound. So reflection is when a sound encounters a surface and then it bounces off, so to speak. We often call this an echo. So if you've ever been in a room that has very smooth walls, doesn't have a lot on the walls, hard floors, you'll often hear an echo. The correlation to this would be if you were standing in front of a mirror or something, a smooth surface, and the light was bouncing off the mirror, and you would be able to see your reflection. Reverberations are best heard when you sing in a room with what? Carpeted walls, hard surface walls, open windows, or none of the above. The trick with reverberation is that if there's an escape or there is an uneven surface, it will be absorbed or scattered. So carpeted walls would cause sound to scatter, which would not amplify the sound at all. Hard surface walls would do a good job of bouncing off sound, and open windows would allow the sound to escape and just go straight out the window. So that leaves us with only one answer that would be potentially correct, hard surface. Too much reflection of sound would lead to sound not being clear, and too much absorption would make it difficult to hear in different areas of the theater. So in acoustics, concert halls have both bouncing sound and absorption of sound, and there's very much a science to it, trying to figure out exactly how to build it to where everyone hears the same thing and that there's no noise. So noise occurs when there's two sounds on top of each other that are not harmonic, and it just gives you this like noise. So you would want everyone in your theater to hear everything clearly, and so it takes a lot of physics actually to work this out to make it give the best experience for everyone. What type of room would you be best to prevent echoes? So this is the opposite of the previous question. What type of surfaces would absorb sound or scatter sound in every direction, which means that it hides it. You can think of it in the same way of like, what would you see your reflection in? If you had a really shiny painted wall or a very shiny floor, you can maybe see your reflection in it, but you would definitely not see it in a carpeted floor. Refraction of sound. So refraction is bending of sound. And interestingly, sound actually travels at different speeds and different temperatures. And what this causes is if you have an area where there's two different temperatures, the sound will actually bend due to this changing of velocity. It's kind of like trying to turn the corner with a trailer. So the trailer kind of lags behind and kind of swings out of the path. And that's what's happening here. So when there's warm air down below and cold air up above, the sound will bend towards the cold air. And in both cases, actually, it's bending towards the cold air. So if you have warm surface and cold air up above, the sound will actually travel up. And potentially, you wouldn't hear it being a distance away that you normally would hear it. If you have the opposite, where you have cool air below and warm air above, the sound again bends towards the cold air. And so you might actually hear a sound further away than normal. This happens on lakes and ponds. So if you are in a boat on a cool lake and it's a little bit of a warm day, the sound carries because instead of it kind of going up and away, it curves back down towards the cold surface. So what is refraction? Refraction, once again, was the bending of the wave, the sound wave, and then what causes it? By this, in this example, the change in temperatures. Also, wind can affect it because wind carries temperature, so that's kind of really the same thing. Refraction of sound. When the air near the ground on a warm day is warmed more than the air above, the sound tends to bend what? So remember that the air bends towards the cold air. So if the warm air is on the surface and the cold air is above, which way would it bend? Next question. In the evening, when the air directly above the pond is cooler than the air above, across the pond, sound across the pond tends to bend which way. So this is cool air on the pond, warm air above, and the sound will bend towards the cold air. All right, sound waves can be used for many different things, and in medicine, they're used to see inside the body. The densest part of the body reflects the most ultrasonic waves and makes them appear bright on an ultrasound scan. This image shows the side view of a baby. You can see the skull, spine, ribs, and bones of the face. So taking a look at this picture here, this is an ultrasound of a baby that is in the mother's womb. This is the skull. So this bright outline, that is the skull. You can also see the bones of the face right here. You can see the spine. You can see parts of the ribs and a hand or a foot right here. So what happens is the denser tissue bounces the sound off more, and it comes back as a brighter spot in the image. Now, X-rays are similar, okay? So sound waves is sound waves traveling. It's a mechanical wave. It's a compression of the medium that kind of vibrates through like that, or like this, I guess. But light is actually a transverse wave, okay? And an X-ray is a type of light wave. Yesterday, you watched two Edpuzzles on the electromagnetic spectrum. X-rays are in the electromagnetic spectrum, and they're very high energy. And so a sound wave is essentially like you're standing and someone's talking to you. So you're being hit with a sound wave. An X-ray is one of the things that comes from the sun that's very deadly to humans. In very small amounts, it can be used in clinical settings to see your bones or see parts of the inside of your body, but a large amount of it will very much damage your body. In fact, Marie Curie, who was one of the scientists who really discovered X-rays used to see inside the body, died of cancer because of the excessive exposure to X-rays. So it is dangerous. It's radiation, it's electromagnetic radiation, which the higher the frequency, the more energy it has and the more dangerous it is. So you have to use this carefully. Now, they do work very similarly. So in an ultrasound, you're sending sound waves into the body that reflect and refract off parts of the body, depending on their density. In an X-ray, it's very similar, but the difference is that with an X-ray, you're seeing the spots that didn't allow the X-ray through. So when you look at an X-ray, you have a black, dark background, and then you have the whiteness of the bones in the image. And the way this is determined is you have a sheet below that registers the X-rays and essentially is reactive to it. And so when the X-rays go through, if it's bone, they don't go through as well. And if it's soft tissue, it goes through easily. And so on the film underneath, it's exposed to different amounts of X-ray. So in the places where the body is more dense, not as much goes through. And so that leaves an impression, an electrical impression essentially on that membrane that you're using to detect the X-ray. So they're similar, but a little bit different. Ultrasound is a refraction type of thing, and an X-ray is more of a what does go through and what doesn't go through type of thing. But they both involve both of those factors: the sound or the X-ray going through the subject, and then also bouncing off of it. All right, reflection and refraction of sound continued. Dolphins actually emit ultrasonic waves, and they use this to navigate. So like sonar. Sonar is a type of navigation using sound waves. Sound travels, bounces back, and you're able to gauge that distance. So if sound is ultrasonic, is it higher in frequency than we hear or lower? So you may have to roll up to find the answer to that. Or possibly Tuesday's lecture included that conversation. Okay, so at this point it says watch Edpuzzle Physics Breaks a Glass. Now, if you've already watched it, good. If not, I would pause the video right now and go do this Edpuzzle. All right, now that you've watched the Edpuzzle on Physics Breaks a Glass, forced vibrations. Forced vibration is setting up vibrations in an object by vibrating force. So if I take a tuning fork and I pluck it, or I take the string of a guitar and I pluck it, I'm putting a force on it that's causing it to vibrate. If you've ever been in a building with a very loud, heavy machinery working, you can feel the vibration in the floor. So question 10 is, what causes the wine glass to break in the Edpuzzle? So that just to see if you were paying attention, go back and watch it again if you need to. Natural frequency is the specific frequency of an object that it vibrates at. And this is based on many factors, including the material it's made out of, the shape of the object, the elasticity of the material, and the combination of materials that something is made out of. Now go watch Edpuzzle Resonance if you have not already. Okay, coming back. Resonance. So resonance is the phenomenon of when you force something to continue vibrating at its natural frequency, and it's like a rhythm. So if I was pushing my daughter in the playground, there's a certain point where I'm supposed to push to actually make her go higher. If I push her at the wrong time, I essentially slow her down or I do nothing. So as the swing is coming towards me, I don't want to push it until it's all the way up. Because if it's in the middle and I push it, all I'm going to do is slow it down if it's coming towards me. But once it reaches the top of the swing, if I take right then and I push it as it goes back the other way, I'm adding energy to it and amplifying that frequency, causing it to swing higher. But there's that one specific time. If I push it any random time, I'm not really doing anything. If I push it when it's swinging towards me, I'm slowing it down. So I'm not actually increasing the volume of the energy. But if I push it right as it starts to go away from me, that's when I can get the most energy into that swing. And many, many objects have that. This one is one that is particularly disastrous. It was the Tacoma Narrows Bridge collapse, and I believe it occurred in 1939 and 1940, right around there. It's in the video, so when you watch the Edpuzzle, you'll see the dates. But it was this bridge they built in, I think it opened in July or November, and it was destroyed within less than a calendar year. So I think it opened in November and closed and was destroyed in July of the next year, because it was a windy spot and the wind hit it at just the right velocity to amplify the swing. So just as when I'm pushing my daughter on a swing in the playground, I'm pushing it to increase her velocity and make her go swing harder and harder and harder. And that's what happened to the bridge. The bridge actually started swaying in its natural frequency, and the wind was blowing just so that it made it more and more and more. And eventually the bridge could not hold itself together, and it fell apart. There were no human lives lost when the bridge collapsed. Luckily, it took a while for it to fall apart, so everyone was able to get off the bridge. There were a few cars that fell into the river, and there were, I believe a dog. Very sad for the dog, but they couldn't get the dog out and it wouldn't leave the car, so that's what ended up happening. And anyway, watch the video. It's pretty interesting. It's a couple minutes long. And remember, I'll be checking the Edpuzzles. There's 3 of them today for your participation in those assignments. All right. Have a great rest of your day. Thank you.